Hello everyone, welcome back. So, in the last class we saw that in the finite volume with unstructured grid you can use this flux update formula which can be given like this. Let us say if you are using the forward order. In general you have basically you can use any du by dt scheme. So, you can use Runge-Kutta third order, fourth order, but all you need to calculate is basically this part, okay, which is the perpendicular flux, okay, on an interface, and you multiply with the area, okay, area vector, and then you basically sum over all the faces. So, for example, this is one of the face, you need to get the flux value here. These are our cell centers I and j, and you might have cell here also, here also, here also, and they will go to all the boundaries that you have. So, if you want to update to this cell, for example, so you will have 3 faces 1, 2 and 3, right. So, on all these 3 faces you calculate the f perpendicular, multiply with this area vector, and then you divide with the cell volume. You add it for all the faces and then divide with the cell volume, and then use any time stepping scheme. Now, to calculate this f perpendiculars, you are getting the value from left and from right, just like we had for the structured grid. We had this I and I plus 1 and I minus 1, okay, I plus 1, sorry, I minus 1 and I plus 1, right. So, you have basically things coming from left, and then basically something going from left to right and right to left, right. So, you if you want to calculate the flux update here, you need to take the contribution from both of these. Similarly, you have to take from all the faces. That is the that is how we do in the finite volume, and because the grid is unstructured. So, you have to take the area normal there, right. So, now if you get the flux from the left, which is basically f u l, okay, and you are getting the flux from the right, which is f u r. So, how do you calculate the unique flux at the interface? You need to have a unique flux, okay. So, as we discussed, you have to solve the Riemann problem there, okay. So, let us say if you start with some schemes that we have discussed, let us say if you use the central scheme, right. So, it is just the average of what you are getting from left and right, but as you know that this is not TVD, okay, this is unstable also, okay, this is unstable for convection, but for the diffusion scheme, let us say you want to solve del square u equal to 0, okay, something like this, okay, some Poisson problem or the Laplacian equation, or purely diffusion problem, you can use this central diffusion scheme. So, that is one of the schemes. Let us say you are doing for hyperbolic flows, okay. So, then there is a non-linear convection. So, then you can use, for example, this Ruzhanov or the local Lex-Frederick scheme. We have discussed this earlier. Okay, it is highly diffusive, but this is one of the schemes that you can start with, because it is normally very stable. Okay, so generally, if when you start writing codes in CFD, you will realize that the schemes which are highly stable, they are highly diffusive also, highly dissipative also, and the schemes which are very high order or basically very accurate, they are also very finicky. Their time steps should be very small. For example, if you are using let us say if you use open form kind of solver, right. So, you have basically row central form, right. So, they use some kind of modified central differencing scheme, okay. So, there the time step required is very small, the lambda has to go to below 0.3 or 0.2 the CFL number, right. So, the scheme is more accurate, then you have to have basically the delta t also honoring the requirements of this high resolution or high order schemes, right. So, that is why if you want to begin, you can start with the scheme which is very diffusive, but also very stable. So, this is the Lox-Frederick scheme, where we have basically a central differencing of this part, and then you remove this part, which makes it very stable, okay. And then we have row scheme, and we have discussed this row scheme in terms of the wave strength, okay, and the wave speed, okay. And so, you have basically the central differencing part, or then you take out this part. So, that becomes the row scheme, right, and you know all these things, lambda, alpha and k. So, wave speed, wave number, sorry, the wave and the wave speeds and the wave strengths. So, all these things you know from your Euler equations or Navier-Stokes equations, mostly Euler equation, right, because for the diffusive part, for the Navier-Stokes part, the viscous part, you can always use the central scheme, okay, that will be for second order, right. So, you can use this row scheme there to solve it, right. So, what are the requirements for the delta t here? Okay. So, if it is a simple finite difference, you know, right, if it is 1D, then lambda is equal to C delta t by del x, that is the CFL number, and that is usually less than 1 if the scheme is explicit, right. So, you calculate delta t as lambda delta x by C, and C is representative wave speed, the maximum wave speed that you have, right, because you want to get the minimum delta t, so that it is stable everywhere. So, what you do, you choose a CFL number, okay, you have some grid size that you have, okay, and usually if the grid is non uniform, then this is delta x minimum, okay, and this is C max, what is the maximum speed that you have. So, that you get this delta t, which is the minimum of all. If you increase the value greater than this, then there is a chance that the code may blow up, right. So, what we can do that, taking the q from here, what we can define local time stepping. So, we want to have something for so lambda you will be taking. So, lambda is lambda, and then for the length scale we can divide the volume by area. Okay. We will do that a cell may have many faces. So, we will have volume on top, and then we what we do, we will multiply this u dot n f plus a. So, this is the maximum speed that you have. Okay, this is the normal velocity magnitude plus the speed of sound, this is u plus a. If you recall in Euler equations, we have waves like u plus a, u and u minus a, right. So, we will take the magnitude of this. So, this is positive and plus a, which is always positive, and multiply by this a f, and then we will sum across all of the faces. So, this is one way of doing time stepping, but you can also define your own maybe length scale and define it in a slightly different way. Okay. Sometimes you can have, let us say, delta x, let us say you have the volume, you know, okay. So, volume to the power 1/3, that can also be one of the possible time length scale for getting your delta t, okay, and you have to take the minimum of that. Now, this is this will be different for every cell. So, this is delta t I, right. So, you have for every I you have number of phases, you calculate it, and for every I you have the volume, and you can do the local time stepping. So, this is good for steady state solution, because in the steady state what happens is that all you care is that how fast your you get the solution convergence. So, you can start from, let us say, mass some value, let us say I would say 1 or something like that, and it goes to, let us say, 10 to the power minus 5, okay, and then you say it is converged. Similarly, you can have the momentum, okay, and then you can have maybe x momentum, y momentum, and then you can have energy, all these things are there, right. So, all you care is that how fast you can reach to this convergence level, whatever you choose, let us say 10 to the power minus 5, right. So, your different cells may be moving at different time steps, and it ultimately all of them have to go to this stage where your d by dt is going to 0, right. So, you have this Navier-Stokes equations or the Euler equations, where you can write everything in terms of du by dt is equal to everything in terms of d by dx plus d by dy, okay. So, let us say df by dx plus dg by dy, and so on and so forth, right, minus. So, if you the problem is steady state, this thing will go to 0, but we will not do it immediately, okay, if you, because we do not know the solution. So, we will do it in an iterative manner. We will not consider it to be 0, we will start with some initial condition, calculate these values, okay, using either finite volume or finite difference, okay, and then use any scheme. Let us say if you are using forward Euler, then basically u n plus 1 minus u n by delta t, right. So, what you expect that as the time increases and as the solution converges, the difference between u n plus 1 and u n goes down, and that is what we are plotting here. So, when it is 10 to the power minus 5, you can say that the difference between u n plus 1 minus u n is order of 10 to the power minus 5, right, and this u can be mass, momentum or energy, right. So, this is what you care about in the steady state problem. So, if you have a grid like this, and you have basically different kind of grid cells, and there are different speeds, different time delta t and so on and so forth. Okay, so delta t1 can be different from delta t2, from delta t3, okay, delta t4 and so on and so forth. But all of them are basically, you know, that they are all going to march towards the convergence if your scheme is right and boundary conditions and everything is right, right. So, then you may not have to basically choose a minimum delta t. On the other hand, if you are working for a problem where you are interested in basically what is the behavior at a given time, normally the transient problem or the unsteady problem, right. So, let us say you want to find out, you started the simulation with t equal to 0 and you want to find out what is the value of t equal to 0.5. So, all of the cells should have I mean all the flows in each of the cells should have moved to t equal to 0.5, and they should have moved to that point with a constant time stepping and every time step, okay, constant delta t in every time step. So, what you need to do is that you have to take minimum of all those delta t I. Okay. So, you calculate the delta t at every cell, okay, and then you basically take the minimum of all those things and use that delta t I for marching in every single cell. So, that is called the global time stepping, right. So, you can use this minimum of all delta t I and we call it as global time step, and this is good for the transient physics. Okay. So, I mean these things are self explanatory, and you know it that this is the volume, area, and u dot on is magnitude normal to the phase, the speed of sound which is always positive, and the CFL number which is typically less than 1 for explicit scheme. Okay. So, now we have discussed about the flux scheme and the time step, and we know how to calculate fluxes. Now, one thing that we have been discussing, that how do we ensure that the upwinding is respected. Okay. So, you have a certain direction of wave and you have to respect that direction, that is the upwinding that we have discussed earlier, right. So, we know that on an unstructured grids the flux is always evaluated phase by phase, right. So, at every phase you will calculate the flux, okay, based on the left and right cell, okay, and then you add all of these with I mean after multiplication by area and the normal vector to get the total flux in the cell, right. So, what we need to ensure is that the way you are choosing left and right, so u, l and u r, they should be consistent. You could choose l here and r here, or you could choose l here and r here, right. So, which one is correct? So, the correct way is that which respects the upwinding, right. So, we are basically trying to enforce it by called flux splitting, which we already do. So, basically take an example, let us say there is an scalar reduction case, okay, delta dot a u equal to 0, or a may be a vector, it may be a constant. Okay. So, let us say at a phase between left and right, it can be any I or j or j or I. So, your flux will be a dot n f into u f, right, that is what we discussed, right, and yeah, you may have to multiply by area there. Okay. So, a dot n f can be written as a n. Okay. So, if it is let us say, let us go back to our structured grid, because that gives you I mean it is easy to interpret there compared to the unstructured grid, right. So, if the convection speed is this way, so if a n is greater than 0, then this should be your u l and this is your r, right. On the other hand, if the convection is from this to this side, then this will be left and this is right. Okay. So, if it is going from this to this side, your phase value, whatever value that you have at the phase, will be basically what is coming from the left. If a n is less than 0, then it is whatever value coming from the right. So, you can write this, you can combine both of these, you can write as a n plus minus is half a n plus minus mod of a n, okay, and then you can basically define your flux for, and it will automatically take care whether it a n is positive or a n is negative, okay, and accordingly it will select whether it is u l or it is u r. So, both I mean so this and these are same. I have just written that this one is written in terms of the flux splitting here. Okay. So, all you need to find out is what is the value of u l and what is the value of u r, and for that you need to know what is the left and what is the right. Okay. So, it only depends on the a dot n f, okay, which is the normal wave speed. Okay. In the case of multi-dimensional flows and the vector equations like Euler equations, it is translated to the wave number, the wave speed that we have been getting, right. So, you have to look at the wave speed lambda k, okay, like we got this characteristic speeds, and depending on what is the sign of that, you have to do the upwinding. So, you have to select the left and right. Okay. So, if we do not have this I j k, so you have to depend on the phase normal, okay, and the distance between I and j. Okay. So, you have to basically choose a left and right that physically influences based on the wave propagation. Okay. So, you have to define NF usually from I to j, okay, and left is from I, right is from j, and then you calculate this V n equal to u dot NF. Okay. This is what we discussed, and depending on what is the direction, okay, if V n is greater than 0, if this u dot NF is greater than 0, the flux is F u L. If it is less than 0, then flux is F u R. Okay. So, this is how you basically ensure upwinding in any arbitrary grid. All you need to find out is what is u dot NF. Okay. So, your area normal is defined at every single phase, okay, and you calculate this vector u here everywhere, okay, you do u dot NF, u dot NF, okay, and depending on what is the value, it is greater than 0, it is positive or negative, you select the accordingly. Okay. So, that is how you calculate the upwind flux on the phases. Okay. So, this is how you do upwinding, but the one thing that is still remaining, that how do you do reconstruction. So, what do I mean by reconstruction? So, recall that we basically change that the piecewise constant value to piecewise linear value to get the second order, and with that we also had to have a limiter, right. So, instead of having a picture like this, okay, in this list I minus 1, I and I plus 1, okay, which is a constant value, what we had done is basically this and this and this, right. So, we have basically replaced with the linear value. Same thing we are going to do in cell also. Basically, we need to have a linear reconstruction from the cell center to the face, okay, because eventually you have to calculate all the fluxes on the face only, right. So, let us say you know the gradient at I, okay, let us say you know the gradient at I. So, you can calculate the value of f, I mean at phase f, and let us call it L, and this is R. So, this is coming from I, it gives the left flux, and from j you get the right flux. So, what will the value of L? That will be, let us say u L will be, you have the value, whatever value that you have, u I plus the gradient that you have, which is delta u I, okay, and dot whatever the distance that you have, R f minus R I. Okay. If you want to write in a scalar way, so then it will be basically u I plus del u by del x at I, okay, and then basically let us say this is my distance delta x, okay. So, this is my delta x and delta y, okay, if I have a global coordinate system like this is x and this is y, okay, and plus let us say del u by del y, you need to have the gradient in y direction also I, and this will be delta y, right. If you are 3D, then you have to have the gradient in the third direction also. Now, the question is how do you calculate gradient here, right. So, if it is a simple structured grid, okay, and then you can basically calculate the gradient. So, what we discussed earlier, that you can look at the cell to the left here or the cell to the right here, and you can calculate based on either. If you are using min mod, then you have to select the slope which is minimum, okay, and similarly we had basically slope definitions from other limiters also, right. Or if you are using let us say beam warming or Lex Van Droff or from scheme, you have certain definition of upwind or downwind or central way of getting the slope, right. So, how do we basically get slope in the unstructured grid, right. So, basically what we are looking at is what is the gradient del u I and basically del u j, okay. So, where u is the gradient at the cell center calculated using least square or green Gauss. So, basically we are going to discuss two approaches, one is called least square, other is called the green Gauss, Okay, so these are the two most common approaches which are used in calculating the gradients for these unstructured elements. Okay, and if you, for example, if you use Fluent, you will have this option that you want to select the least square option or the green Gauss option. Okay, so let me look at both these approaches one by one. Okay, so again, I mean, before we go to these approaches, okay, the least square or the green gas approaches, uh, let's say that we know the value of the gradient, but we cannot use the value of gradient uh, right directly, right, because if you use the value of the gradient, then this is something called unlimited flux and this will have those wiggles. Okay. So, if you have a discontinuity like this, you might have wiggles here or here. Okay. So, depending on this may be Lexman drop, this is maybe beam warming or the from scheme, right. So, that is why we had to have the limiter, right. So, you cannot directly use it. So, you have to basically limit it. So, you have to multiply with the limiter, value with the limiter, right. So, how do you basically, what are the different limiters? So, we for the structured grid, either in finite volume or finite difference, we have discussed the limiters like min mod or the super B. Okay. But I mean those limiters will be useful because they have a clear definition of R, okay, which is basically ui minus 1 by ui plus 1 minus ui. Okay. If let us say the C is greater than 0. Okay. The basically delta u of wind by delta u of the current, that is what we have been telling. Okay. But that is not true in the case of unstructured grid, right, because I mean there is no there are no 3 connectivity I plus 1 and basically I minus 1, right. How do you so the limiters have to be changed, but there has to be limiter. You cannot solve a problem without limiter because it will definitely lead to the wiggles if the problem is not smooth. If the problem is smooth and there is no big discontinuity, then maybe the limiter is not necessary. You can use very high order scheme also without this limiter, but if you have discontinuity, then definitely you have to have the limiters, those limiters. So, let us see what are the limiters which are generally used. Okay. And another thing is that since that cell can have many phases 1, 2, 3. Okay. So, you have to basically you can calculate the limiter or you can have the limiters at every phase phi 1, phi 2 and phi 3. Okay. And then you have to select the minimum of these all limiters. So, minimum of the whatever the slope that you are getting will be used to basically update the formula or basically to update the value at the phases. Okay. So, so there are basically two limiters. One is called the Barth and Jesperson limiter, BJ limiter, and another is the Venkat Krishna limiter. Okay. So, what we will do, we will basically discuss these limiters in detail in the next class. So, ultimately what we want to have is that you should have a definition of the limiter which works on an unstructured grid. Okay. And we will see that BJ is kind of inspired from the min mod limiter. Okay. And the Venkat Krishna is kind of inspired from the von Leer limiter. Okay. So, we will discuss both these limiters in the next class. Thank you very much.